So what I wanted to do today was to review the, I would say, open issues that are left after the Augustine report and presidential budget decisions. And in other words, I'm not going to spend a lot of time talking about things that are essentially sort of closed and done. And to give you a sense of the reasoning that we did last summer, the information that was available to us, and in about a dozen places highlight, I have charts that I call behind the scenes, that you get some sense of the information that we were actually looking at in order to come to the higher level decisions. So this is just the charter from OSTP. The highlighted words are suitable options. You'll notice that the report does not make any recommendations. It creates options and evaluates them, and the decisions were made beyond us. We did spend some time in the beginning talking about why we explore. I don't think there's anything particularly earth-shattering on this chart. We did try to differentiate these more tangible benefits, including exploration, preparation, involvement of science, technology for space and Earth, because we knew this was an important issue for the administration. Economic development, again, an important issue for the administration, as well as the less tangible benefits that are fairly well understood. I think that the more interesting thing is that this rather diverse group of 10 people, including generals and CEOs and so forth, very quickly and unanimously agreed that we should try to cast Mars as the ultimate destination of the inner solar system for a variety of reasons, which are sort of the obvious ones. But the idea that this quickly converged as this sort of vision in the distance as the destination, but not necessarily the near-term goal, materialized quite quickly. And therefore, this and the previous pages of the goals should drive thinking about destinations and systems. As you know, we did a work which was actually built upon work that had been done in ESMD over the last few years about defining metrics, and we sort of raised them up to a higher level. These are the 7 which are sort of an expansion, a slight expansion of the ones within the global exploration strategy. And you'll notice that they correlate very well with other important policy documents. Reading across the top is the Space Act of 1958, the Vision for Space Exploration from the Bush administration in 2004, the Global Exploration Strategy, and the guidance from OSTP. So this would be recognized as both historical Democratic and Republican guidance. And the fact is that there isn't much disagreement on why we have human space exploration, that it's to do these things. So there's fairly bipartisan and historically consistent advice here. At the next level, those are previous 7 were what you might call the benefit areas. These are more or less the cost, risk, and resource areas. These were more specifically enumerated in the OSTP guidance, although some of them are traceable to the Vision and the Space Act. But they're the normal things that engineering managers think about. Schedule and programmatic risk, basically hazard, workforce impacts, programmatic sustainability, and cost. And as you know, the committee developed rubrics on a 5-point scale to rate each of the integrated options on each of these 12 parameters, and did so in a public meeting. The initial intent was that the baseline constellation program would score about a 0, so that it was sort of referenced up and down from constellation. However, in the details of the scoring, we did find that we developed sort of an understanding that caused a few of the constellation scores to not be 0, but be consistent with the rest of the scores that were given. So, yeah, in some senses, the whole talk is on this chart and the next one, and then I'll go from there. Setting aside the shuttle and the means of getting people to low Earth orbit, which of course are very important things and dominate much of the operating costs and development costs. Once you're sort of in space, the decisions that were in front of us basically were, what do you do with the ISS? Do you go to the moon? Do you do this thing roughly called the flexible path, or you go to Mars? And very rapidly, the consensus evolved and I'll say privately, as private as this forum is, surprisingly, that the ISS was actually on the critical path to do the rest of the things. This was not a committee of shuttle huggers, station huggers. There were people on the committee who were on public record as saying, you know, we don't need the ISS, we should shut it down as fast as possible. So this is sort of Nixon can go to China. You know, that the internal dynamics were such that one by one, 12 angry men, you know, the committee sort of came around to understanding the integral role that the ISS had in further space exploration. It's got a technical dimension, it's got a political dimension. The political dimension is the international partners very clearly said to us that if the United States ever wants to have the right to lead an international space endeavor again, it's got to make good on the moral obligations of operating the International Space Station for at least a while. And the technical dimensions are that as time went on, we realized that there were, in fact, many things that you could do on the ISS that would actually help you prepare for preparation if you actually knew it was going to be around for a decade and could count on it. Up to and including, I would say, the suggestion that first came from the Russians, which was that it was their intent to operate at least their part of the ISS well into the 20s, and that they viewed it as the base from which they would do further exploration, which was, of course, one of the original intents of the ISS. It was going to be the staging base for going beyond low Earth orbit. So I think we should re-expand our view of the ISS as not only what can we do there, which is of developmental value, you know, work on fuel transfer and storage technologies and understand microgravity remediation and so forth, but even as far as saying what can we do with the ISS in terms of initial operational capability beyond low Earth orbit, which of course raises the question, do we want to go into 51.5? And most of us who have grown up thinking about shuttle performance severely over-penalize the performance of launch transportation systems when they go to 51.5 because of the mechanics of the shuttle and how payload is accounted for. You know, we think of like a 10% penalty associated with going to 51.5, where in fact for a non-shuttle, a non-reusable base system, it's only a few percent penalty for going to 51.5. Okay? So this sort of puts the ISS in an entirely new light. Now, of course, I'm not going to talk subsequently about the decision about the ISS. It was made. It was a rational decision. So then, now we're in the upper right-hand corner. You go to the ISS, and then what? Well, the next thing that happened is that we realized that going to the moon was not the first thing to do. Despite the advocates' position and going to Mars, I'm sorry, going to Mars was not the first thing to do. It's too expensive, it's too risky, we don't have the technology and so forth. So Mars becomes the ultimate destination, and then you say, well, if you're not going to go immediately to Mars, do you go to the moon and then to Mars, or do you go to something like the flexible path and then to Mars? And the reasoning here is, if you go to the moon, you learn how to work on a planetary surface and land and take off and push dirt around and extract resources and so forth. But you would never have been more than 3.5 days from Earth. And you would not have actually learned to work in the free space that will be required for 200-day transit to and from Mars each. So if you had gone to the moon for a decade and then you were the president and being told that the next step is to go on a 900-day mission, would you do it? And the answer is probably not. You'd say, well, isn't there an intermediate way where we can develop more experience in deep space before we go on a 900-day mission? So that's what the flexible path does. So what we got to is in the lower left-hand corner, which is the realization that on the way to Mars, you will probably do something like go back to the surface of the moon and something like go along the flexible path. And it's really just a matter of which sequence you do them in. Because you need to develop and demonstrate both of these capabilities to work effective, to really have a credible chance of landing humans on Mars in a sustainable way. And I'll come back to the sequence issue later. The other chart, which is actually not in the presentation, and in fact I made up in the last few days, but the words that document this are in the report in various places, is the what I call the envisioned transportation infrastructure. that there's some system that gets us to low Earth orbit, which is probably a super heavy, to distinguish it from the way the ELV people use heavy. And we rationalized, and I'll get back to it, something like a 50 to 60 ton minimum throw weight to LEO. That in the earlier stages, you would use this vehicle, which has the capability to put something in the range of 20 to 30 tons into escape, together with an in-space propulsion stage and a CEV or a crew capsule and a HAB to go places and do things that you wanted to do. In later stages, you would do some sort of refueling, either from a tanker or a depot, and then ultimately you would get to building and operating planetary landers. So this is what I would call a notional transportation infrastructure, which I'll reference. And there's a very clear statement in the report that says a prudent strategy would be to develop a heavy lift launch capability which had initial capability which was important in the absence of refueling, but then became enhanced when refueling became demonstrated, or words to that effect. So the key questions in the report are these. What do you do with the shuttle? Not going to talk about it anymore. What are you going to do with the ISS? Already mentioned it. And I'm going to focus on the remaining three: the heavy lift launch system, the crew launch system, and the strategy for exploration beyond LEO. Plus, implicitly, there was a budget assumption. And the approach of the committee was to fix performance and budget level, and then use schedule as the independent variable. Right? So we looked at when dates occurred as a measure of sort of what the relative merit of what things were. And that got us, of course, to these integrated options, which were never meant to be exclusive. In other words, we couldn't give the president 5 decisions and then say, but you can only pick these combinations. But in order to do analysis, we needed to have some integrated options. These are directly from the report. Now, here's the first behind-the-scenes look. In developing these options, we actually explicitly thought about sort of a function-informed decomposition of the transportation architecture. And there are about 4 functions here: get the crew in orbit, get the cargo in orbit, operate in near-Earth environment, and explore beyond near-Earth environment. And you can see the boxes are the pieces that we normally think about. The shuttle, of course, does both crew and cargo. We're largely going to separate those into the heavy that would do the cargo, and here are the classes. DSDV is directly shuttle-derived vehicle, to give the sense that it's more direct than the Ares 5 family of vehicles. ELV crew options on the left-hand side, and pathways and vehicles in the uppers. Now, here's another look behind the scenes. That formulation of the problem was actually based on work that ESMD had sponsored in my lab, which is called decision-based or architectural decision graph theory, where you try to identify the key decisions and you place the options or the choices for each decision. So this is actually the decision graph that I drew last summer but never showed anybody for the study, where there are these 5 key decisions and then there are the options. And if you have I'm looking for a pointer here. This will work for the people in the room, but no, it won't work for the people in the room because it's not visible on the screen. But if you look at the middle row, the middle blue row of the grid, if you fixed a value in a decision in all the other rows and varied that decision, that would be sort of classical trade study. You know, let's set where we're going, and let's set the crew capsule, and let's set the what we're doing with the ISS, and let's vary the heavy lifter. We did a little of that. If you sort of take traces top to bottom through the decisions, you actually produce the integrated scenarios. And the integrated scenarios were chosen so that they span the entire space of decisions. So if you actually look through the 8 scenarios, they have reasonable combinations of budget, launch vehicle, et cetera. And then the third option, which is what I actually do in my work, is to parameterize the whole problem and search comprehensively through the search space. We didn't have time to do that. So that's a little bit of the reasoning we were applying, and in fact, in the last year, we've been working on applying that to the lunar surface system architecture problem, as some of you may know. So here's the now what's numerically the fifth decision, the first one I'm going to talk about, which is where do you go? And we've eliminated Mars first and left in the option space Moon first and the flexible path. That is, in the report we did that. Now, when you actually start thinking about these destinations, they sort of lay out in this delta V and duration. Vertical can be either thought of as mass or duration space. And the thing you realize is that, and these are delta V changes in kilometers per second from low Earth orbit, that there is a whole set of destinations if you don't go into the deep gravity wells of the larger planetary bodies, the Moon and Mars, that you can get to for considerably less delta V than going in any of the deep gravity wells, either the Moon, which is sort of the middle band, or Mars, which is the right-hand band. So the motivation technically for the flexible path is something like what can you do with a few to a handful of kilometers a second of delta V and not having to build a dedicated lander before you subsequently build a dedicated lander. And everything up to a Mars flyby sort of falls in that band. So we did these three, we created actually 5 scenarios A to E last summer. One of them was called Mars First. And I think an interesting result from the Mars First is that we challenged the Mars team, which was scenarios C and D, to answer the question, why would you ever go to the Moon if you had to pay for it? Which is actually a quite different question than, we're going to the Moon, how can we use it to prepare for Mars? Right? Now it's sort of the reverse question. We're going to Mars, what would you do at the Moon in order to prepare? And they did an interesting study where they went technology by technology and concluded that there was no technology the demonstration of which necessitated going to the Moon. That you could do Earth simulation, orbital simulation, model systems on Mars, and never have to go to the Moon. So the only rationale that they presented for going to the Moon, if you knew that your intention was to go to Mars, this is a NASA JSC-led study, by the way. Right? This is Brett Drake and gang, was that you would use it as a dress rehearsal. You would take the entire built-up Mars system and do a system validation test on the Moon. So it would look something like this. This is sort of photoshopped from the normal DRA 5.0 drawing. I didn't do this. This is a JSC or NASA work product. So you notice that it's about the same configuration of launch vehicles that would go to Mars, except they go to the Moon. And then you slightly modify the lander. It's an easier landing job on the Moon. And you slightly modify, if needed, the rovers. And you test them for 60, 180, 360 days on the Moon. And at any time, if there's a problem, you come back. So this isn't the use of the Moon as some sort of vague technological demonstration. This is actually the use of the Moon as part of the test program for going to Mars. We had 2 scenarios for exploring the lunar surface, so that was the sort of the interesting result that came out of the Mars study, which is you would use the Moon, but you'd use the Moon for a full dress rehearsal. If you go to the Mars study, the Moon study, the essential answer that came out of this was, at the level we were doing our work, you couldn't tell the difference between any lunar exploration strategy. Build a base, go to sites around the Moon, which actually the lunar surface system architecture study was sort of moving towards in 12 and 13, scenarios 12 and 13. The cost differentiation and the value differentiation just weren't noticeable at a policy level. So the important text in the report here is, if we choose to go to the Moon, you really leave it up to NASA to figure out how to do that. It's just the subject of more detailed analysis. But this is the notional scheme for how you would go to the moon in a more global way, where you do some sortie phases, and then you'd go someplace for 50-ish days, and then you go someplace for 100-ish days, and you go someplace else for 200-ish days, and you develop the capability and to visit various places, and then perhaps decide where to build a base. And as I said, the lunar surface system studies were sort of moving in this direction. Now then we get to the third strategic option for exploration, which is the flexible path. And there is a fundamental difference in thinking about exploration strategy, and this is what this was called, not destination, notice. It's not exploration destination, it was exploration strategy. There's a fundamental difference in strategy here, which is the following, that the way that you initially use humans to explore space is that you use them to go to places where they don't have to go down into deep gravity wells and interact with things like Earth-Sun L2 to service James Webb Space Telescope or NEOs or other interesting small bodies, or the moons of Mars. And, at least initially, you allow them to interact robotically. You interact with robotic assets on the planetary surfaces. So this is sort of go into a standard orbit and send down Class 1 probes. Right? That it's a different strategy for exploration, and it would draw together much more integrally the robotic strategy and the human strategy, because now they'd arrive someplace and work together. So, for example, if you want to get a Mars sample return before you send humans to the surface, when that mission gets costed out, it comes out quite costly. Billions, right? Billions and counting. And much of the challenge in that is that you now have to land a robotic system that can actually send robotically the sample all the way home. Well, if you had humans in the vicinity of Mars, and all the robotic system had to do was get something off the surface of Mars and be a passive target for a human rendezvous and acquisition, you see it shifts the functionality of returning the sample from the Mars vicinity to the human program away from the robotic program, and there's some synergy, for example. So this is a chart which I recommend to your careful consideration. I won't have time to do it justice in the next few minutes. But this was our sort of summary rationale for the value propositions of the destinations along the flexible path. A lunar flyby and the Earth-Moon L1 are basically test missions. These are Gemini. You go and fly around the moon just to make sure everything works. You go to Earth-Moon L1 because it's someplace different than going to the moon. Now, each of these has valid public engagement reasons, which are listed here. Some of them have valid science reasons. For example, there is an alternative way to service assets at the Earth-Sun L points, which is to move them through a very small delta V to the Earth-Moon L1, and then service them there, and then move them back to the Earth-Sun Lagrange points. So by going to the Earth-Moon Lagrange point, you demonstrated that you can get to the place with humans that you would do that mode of astronomical observatory servicing. The Earth-Moon L1 point is the likely place you would depot fuels that were extracted from ISRU on the moon. So that's why we call it the on-ramp to the interplanetary surface superhighway, or the interplanetary highway. The big step is really going to the Earth-Sun L1 and L2 points, which demonstrate the ability to go there and service, but also you can credibly claim that now humans have left the Earth-Moon system, right? The Earth-Sun L points are at about 5 moon radii, roughly. So no one would say by the time we get there that we haven't left the cradle. And then so forth. The NEOs are sort of the obvious destination. And then you get to Mars flybys, Mars orbits, Mars moons, and then ultimately the surface of the moon. And you can see rationalized here what value you get starting from the left for exploration, preparation, human research, science, and public engagement. The real rationale here is, I think, the human research column, that this combination of destinations and ways to visit them sort of produces this nice Gemini-like progression of about a week, a couple of weeks, a couple of months, a half a year, a couple of years, that you would demonstrate that humans could live and work in space as you progress through. And, you know, to some extent, the destinations are just the places that allow you to go someplace in a couple of weeks, a couple of months, a half a year, and so forth. So the rationale for these destinations really doesn't hang on any single one of these columns, but rather the sort of the combination of them. And not to mention the first column, which is that every time you make one of these flights, for the exception of the first one, which reproduces Apollo 8, every time you make one of these flights, you've gone someplace new that humans have not gone before, as opposed to the headline reading, "Humans return to the moon 50 years later." So this is our attempt at sort of putting together a rationale, and I commend that to your careful examination, that chart. So here's how it might lay out in a notional, non-budget constrained plan, that you would almost certainly do the test flights to the moon and the L points first. Then more or less the obvious destination is the NEOs, one or several NEOs, and the rate at which we're discovering them would indicate that by 2020 or 2025, there would be one to go to almost any time you wanted to go, I mean, with reasonable windows. And then maybe a Mars flyby, or at that point you do an option and you go to the lunar surface, which is either the upper rung or the lower rung. So this chart was put together at Langley in order to sort of try and convey that the flexible path really is flexible. It's not a, we must do this and we must do this and we must do this. We develop the capabilities to work in deep space or in zero gravity outside the Van Allen belts. We do the obvious few test flights that lead us probably to the near-Earth objects. And then we might decide that we now have the national resources and technology to go to the lunar surface. Or we might decide that the next thing to do is a Mars flyby. Or that having gone to the lunar surface, we then might go and do a Mars flyby and so forth. That there's actually, if you count them up, about 7 logical paths through this, starting with going to a NEO. That it maintains an option space for future planners and therefore implies a capability development that lays in the capability to do these various things. Now, behind the scenes, this is I think the second of these, there was an awful lot of work done constrained by the amount of time we had, which was about a month, by a team led by David Korsmeyer at Ames Research Center on the flexible path. He analyzed with his team about 15 missions, each for 3 different classes of launch vehicles, with and without refueling, and for 2 different upper stages. So you do those multipliers, and there's a lot of cases that these guys ran. And they developed the manifesting and verified the feasibility of the missions. And I won't go into details about the next 2, but generally speaking, the missions are on the upper chart on the left, the lunar flybys, the L missions, the NEOs, the Mars flybys, and so forth. And you can see the data here that was the assumptions that were used in this, and almost unreasonable to any of us. The lower block has all the cargo manifests for all these missions notionally. And one of the things that I guess Phil had to leave, but Nantel and Phil McAllister and I have been talking about in the last few days is putting together an archive of at least the principle of these reports that were presented to the committee, so that they're not just on my laptop and Phil's, but they're actually available, Mike, to your gang.
Actually, and the Independent Program and Cost Evaluation and ESMD are working together. We put together a large database of previous studies. We'd like to take your study and put it in as well.
Yeah.
To that
But actually, what's more important than our study is the studies that informed our studies. Right.
Yeah.
So we'll work on that. So that but this is an example. This is sort of a summary plot, and without having a pointer available, it's going to be a little hard. But the upper left-hand corner is total mission delta V, mission duration, and payload mass. The lower left-hand corner is for the 25, 75, and 125 vehicle classes, how much MLEO there is. And then the right-hand sides are example manifests for the 20, starting at the top, the 25, in the middle, the 75, and at the bottom, the 125 class launch vehicles to LEO. So we looked at flexible path missions down to the level of detail of what launch vehicle would be used, what upper stage would be used, where would they go, and what would the launch manifest look like, to convince ourselves that the things we were proposing were feasible. Our attitude in the committee last summer was that it was essentially a policy level discussion, but the policy options that we enumerated had to be substantiated by at least technical feasibility, if not technical optimality. So we didn't have time to do lots of trade studies, but we did enough to make sure that what we were saying wasn't foolish. I think I'll skip this point. So that was, well, I'll leave it on so you can look at it and say a few words. So just to recap, we considered basically 3 strategies, and they really are strategies, not destinations. What's the strategy for exploring the moon, if that's chosen? What's the strategy for exploring Mars, and what would you do to prepare yourself for that? And what's the strategy for doing something like the flexible path? And the flexible path does not exclude, but defers either the moon or Mars in our thinking. So choosing the flexible path does not give up the moon. It just recognizes that the moon is something you do a little later than you might do if you put your sights on it immediately. But we'll come back and see whether that assumption is correct in a few moments. And then we said, but you really can't do Mars. So you either do the flexible path or the moon. Okay, launch to LEO. This is cargo launch to LEO. And in this case, we enumerated 4 options. Ares 1 plus Ares 5, the reference option. The Ares 5 dual light proposed by the program, a more directly shuttle-derived vehicle, or an ELV like Super Heavy. And if you read the report, you will find that even when we evaluated these, we did not find strong preferences among them, that they all had their pluses and minuses. The next chart just sort of lays it out in a pictorial way that you can sort of reason through the branching here. ELV heritage, which is to say boosters and liquids, or basically the solids, is what differentiates the top branch, and then more detailed things within the NASA family. Now, behind the scenes, there was a pretty fierce discussion going on in the committee about what was the necessary launch capacity. In other words, what's the smallest, biggest vehicle you could get away with? And so here are more or less extracted from the text, the reasoning that we used. Exploration beyond LEO probably requires an annual throw mass to LEO in the range of 400 to 600 metric tons. We've never done that, right? We've never even come close to that. The Apollo era at its peak, between Apollo 11 and about 15, was about 250 metric tons a year to LEO, 2 Apollos, roughly. And the ISS is 350 metric tons, took us a decade to build it, right? So we're talking about 1 to 2 ISSs per year in the era of exploration. So what sets the size of the Super Heavy that you would build to launch that? Well, one thing is you can think about what's the capacity of the entire existing U.S. fleet. We make 10 to 20 launches a year of, let's call them 25-ton class vehicles, 250 to 500 metric tons. It would take the whole traffic model of the U.S. to support exploration with the existing vehicles. Or you would double it, roughly. There's another consideration about what's the smallest feasible largest chunk. In other words, how small can you get the biggest thing? And many people are of the opinion that this is what sets the launch vehicle size. And we actually became persuaded that's not the case, because we actually went systematically through all the chunks, And actually, you don't find a chunk that's more than about 40 metric tons, unless you count the fuel that goes in the vehicles as part of the chunk, right? So if you count the fuel, then you get up into the 120, 140 range. If you don't count the fuel, you're down in the 30 to 40 metric ton range. So that raises the in-space refueling question, and what we really found drove the issue is none of the above but launch reliability. And I'll show you the launch reliability. For reference, the Constellation EDS is composed on orbit of about 60 metric tons of payload, 94 metric tons of fuel, and 25 metric tons dry. So you could actually launch the Constellation EDS on a Delta IV Heavy if it fit in the shroud, which of course it doesn't, right? So what happens is that when you refuel and launch upper stages towards dry, they actually become geometrically constrained, not mass constrained. So you've got to look at the geometric and mass constraints at the same time. In-space propulsion and landers are usually at least 50% fuel, and elements that are thought to be monolithic can actually often be broken up and modularized. So for example, Brett Drake did an analysis where he extended DRA 5.0 to scenario D, and there's a lot of information on here that you can look at. But the basic message is, in the upper left-hand side, that if you carry down the oxidizer, you need a 40-ish metric ton ascent stage. But if you use ISRU to produce the oxidizer, you only need a 20-ish metric ton ascent stage. And that's actually the biggest piece we could find in the system. So if you're sizing your launch vehicle by what's the biggest piece we ever need to launch, it's, you know, on the range of 7 or 8-ish meters, I would guess, and on the order of something between 20 and 40 metric tons. Now, the DRA 5.0 architecture calls for a descent vehicle that has a payload mass of 40 tons and a surface habitat of 40 tons. And we challenged that gang to say, is that really the atomic size, or can you actually cut that up? And in fact, they came back with a quite reasonable scheme where you cut it up, the two things, into 4 things, and you could actually land about chunks of about 20-ton payloads. And now the 20-ton payload of the descent-ascent vehicle does not have the oxidizer in it. You rely on the ISRU on the moon to produce the oxidizer. So if you start going down the route of what's the biggest piece we have to fly, and you neglect fuel, you actually get pretty small pieces. That the reason why the numbers come out 100, 120, 140 tons as the smallest piece is they're all fueled up, right? So that gets us to in-space propellant storage and transfer. It can be done in 2 modes, which I call sort of the tanker mode and the depot mode. That's a detail that we didn't really bother to get into. We looked at all the TRLs for these things and became convinced these things are sort of TRL 5-ish at the minimum. And the things that are TRL 5 can't really advance beyond that without an in-space flight experiment. So they're stuck at 4. I'm sorry, TRL 4. Did I say 5? I've said TRL 4. They're stuck at 4 until you do a flight experiment. All right. So if you want to do this, the next thing to do is to put together a flight demonstration. So now here's the behind the scenes on refueling. We actually did 4 different studies of the benefits of using refueling. Scenario B did one, Scenario C did one, Scenario E did one, and I did one. And we identified 3 modes of refueling operations. The simplest is you just launch the payload on the EDS and you refuel some of the fuel or all of the fuel in LEO. Right. The second one is that you launch no payload on the EDS and you refuel some or all of the EDS in LEO and then assemble the payload on. And the third option is that you launch the payload on the EDS, but the payload is dry, because remember the in-space stages and landers by mass are 50 or 60% fuel. So you could refuel them on orbit as well, right? Now, we didn't actually study very much of the third option. My analysis of mode 1, the launch the payload and burn the fuel in EDS and retank it, produces factors of 2 to 3 increase in escape throw mass. That's what the report says. And mode 2, where you don't put the payload on the EDS and you burn it out, produces factors up to 10, but in practice the EDS becomes constrained by launch geometry. You can't fit that big a vehicle in the shrouds we have. Bill Cirillo on the next chart did an analysis of payload through all the refueling processes to the lunar surface. In other words, how much would the lander capacities go up if you could refuel the Constellation EDS? And the ratios are in the table on the right-hand side. If you can't read them, the lowest number is 2.1 and the highest number is 5.8. So if you propagate it through all the way to the lunar surface, refueling, depending on all the assumptions you make, gives you between about a 2 and 6 factor of increase in payload delivered to the lunar surface. So these are big numbers. You know, the minimum number is around 2, and if you work the system, you can probably easily get 3. You stretch a little more, you can get 4 or 5. Now here's the economics of refueling, and I'm going to talk you through the chart on the upper right-hand side. This is for a LOX RP1 system with a LOX hydrogen upper stage, and this is essentially the gear ratio. This is the glow for a 1 metric ton to escape. C3 is equal to 0. So Saturn 1 is 60 tons. 60 tons on the payload on the launch platform for every ton to escape. And our analysis of a new 2.5 stage RP1 hydrogen vehicle put it at 70. And this is a booster or 2.5 stage vehicle, not a 3-stage vehicle. So that's essentially agreement. If you refueled, that would drop to about 30. So that's about 2.4. If you put the fuel back in, it's almost not noticeable on the 4th line. It's the little orange band. But then if you put Ariane 5 flights in as a known surrogate to launch the fuel, it goes up to the green bar on the far right, which indicates that you can't actually violate the rocket equation, right? If you built one vehicle, it would take 70 tons to produce a ton to escape. And if you refuel a smaller vehicle, it actually produces about 80 tons on a combination of launch pads to produce 1 ton to escape. But what you can do is you can build a smaller vehicle, which then has potentially benefits which are indicated on the left-hand side, potentially lower development costs for the reasons indicated, but almost certainly lower recurring costs, that you have better utilization of facilities, you can amortize the fixed recurring costs over more launches, and most importantly, there's at least the potential that you can share this vehicle with other customers, including the national security space customers. And there's more learning and benefit of scale of production. Now, you don't get to this being a desirable answer if you're thinking about the chart in the lower right-hand side, which is the conventional cost versus payload mass, which is not linear, right? There are economies of size that caused it to bend over. You get fewer dollars per pound to orbit for a big vehicle than you get for a small vehicle. And if you're in that mode of thought, you look at the upper chart about refueling, you say, why would you ever do that? Well, the committee became very convinced this summer that this chart in the lower right-hand corner is not the right one to think about. That in fact the costs of launch are dominated by what we call the fixed recurring costs. You know, what it costs to keep the launch pads running, the staff to put things on the launch pad, all the backup support that's at the other end of the phone to support all these launch vehicles, the manufacturing infrastructure. And in fact, if you look at the shuttle costs in the last 5 years, when we've launched 0, 1, 2, 3, 4, and 5 shuttles a year, you can barely see a difference in the shuttle system cost over 0 to 5. And if you think that the cost of an EELV is really whatever ULA will charge you for it, you're forgetting the $1 billion+ subsidy that the DoD puts into ULA for the system. So if you want to attack the cost to low Earth orbit, you really have to take on amortizing the fixed recurring costs over more customers or more vehicles in some way. And that's what we're trying to do. Now, the other thing that's really important to note, and I would recommend this for close scrutiny, is this launch reliability study that a group of people who I think were head by Langley, Bill Cirillo, and I think included people from Lewis worked on. If you have to launch 400 to 600 metric tons worth of stuff into orbit within a fixed window, and there will always be a fixed window, you'll have boil off or crew standing around or something, then really what drives the size of the vehicles that you need to launch that much mass is the reliability that you'll actually launch it in the window, which is not very good, it turns out. That if you roll a shuttle out on any given day, there's about a 55% chance it'll launch, and then there's some chance it'll launch a few days later, and some chance it'll launch a week later, and some chance it'll launch a month later. And it's interesting that the statistics between the EELVs and the shuttle are pretty similar, despite the fact that one's a reusable and one's an expendable. So it says something about either the way we launch or weather in Florida or all of the above, right? So what we did is we commissioned, first we said that now that you're in the era of refueling, you have to differentiate between critical flights, things with EDSs and landers, and non-critical flights or less critical flights, things with fuel. And you can treat those two things differently in your launch model. So this is what we had the crew do. They did this probabilistic analysis using the real statistics of launch reliability. And they played the game of, if you launch the first one and then start the clock, how long is it before you launch the nth one? And here's their sort of operational mode. You launch the first critical one to start the clock, and then you launch the fuel, and then you launch, when you get it all fueled, you launch the subsequent ones. Now you can say there's other variations of this, and you'd be right. So here's a sample of the data. This is assuming that the critical elements have a launch reliability of 0.985. That's as high as any launch system has ever demonstrated. That's Soyuz and Delta II at the peaks of their operational life. So if you have 3 critical launches of that critical, just the 3 critical things, with those launch reliabilities and real weather conditions and pad conditions and so forth, you get down in the low 90s of reliability. And then if you have 120 days, however, if you're trying to launch all 3 of those critical flights, this is the 0 on the horizontal axis. The horizontal axis is the number of fuel flights. So 0 is just the 3 critical flights, no tanker flights. If you have to launch those 3 critical flights in 30 days, based on current launch statistics, there's a 60% chance you'll do it. And you can imagine the way the statistics go, that if you broke the 400 tons up into more than 3 pieces, it would rapidly deteriorate from that. And then you put the tanker flights in, and they give you the curves going outwards. And you notice that if you went all the way up to like 10 tanker flights, the one that started, the green curve that started on the left-hand side at about low 90s ends up at sort of high 70s. And that's assuming there's at least 1 live spare that you can refly, you can launch through 1 failure. And we did it through 0 failures, and we did it through 2 failures, and looked at all these statistics. So what really dominates the reasoning about what the launch capacity has to be, I think, is this picture, which was, I don't think, understood at all until last summer when the NASA team did this analysis for us. And you really got to dig into this.
That's a huge assumption that you're going to launch another one right away without investigating the failure.
Huge assumption.
Okay.
Right. However, the model assumes, the reasoning assumes they're not critical, right? You're just launching fuel.
But if it's the same vehicle as what you're launching the critical one on.
Oh, it isn't. It's assumed to not be the same vehicle.
Okay.
Right.
Gotcha.
And the tacit assumption is there's several providers. Right? So if a SpaceX one fails, you dial up another orbital one, or another Blue Origin one, or another ULA one. that this is a business that people are in. Okay, that's the end of heavy lift. So, I didn't actually say much in there about whether I thought we should use an Ares 5 or a hydrocarbon stage, because to be honest with you, the committee looked at those and saw pluses and minuses in all of them. I tried to focus more on the sort of generic considerations that you would have in all of those. Crew. We looked at the Ares 1 and Orion. You'll note that we do not recommend that either of them be canceled. As a matter of fact, this is a chart that we briefed the White House with last August. It says ESAS chose a sound architecture under the assumptions of the day. The assumptions being that the Ares 1 and Orion would be available to service the ISS by 2012. That was the timing at the time of ESAS, right? That it would have high ascent safety, high commonality with the Ares 5, good for workforce development, and that we should proceed with the Orion as NASA will need some vehicle for going beyond low Earth orbit regardless of when we do it. We found no insurmountable technical problems. However, Ares 1 will not effectively serve the ISS. If the ISS is canceled in 15, it misses it. And if it's extended, it gets the last few years of the ISS. It will cost $5 to $6 billion to develop, assuming all common costs are carried by the Ares 5. That's a balance sheet analysis. But if you do a cash flow analysis, you find that you have to spend a lot of money before the Ares 1 is actually flight ready. And when operational, by Constellation program estimates, the recurring cost is about $1 billion per launch. Now, that was a very sobering revelation. And I'm going to come back to it later. You believe that? You're looking at that like that's news.
Well, we've heard estimates from half that to a little bit more than that.
Okay.
So we're curious as to the.
This is data we got from Constellation, and this number assumes that the common systems between the Ares 1 and Ares 5 are carried by the Ares 5 budget.
So that's a lower number.
That's a lower number. There's an upper number, which is 1.4, 1.5 billion per launch.
So this isn't marginal, it's also including some fixed costs?
Yes, that's right.
Okay,
That's right.
Yes.
Right. Now, this sort of made us realize, this is three of these is a shuttle program in round numbers. And it made us realize that the people who in 1971 or 2 realized that building heavy expendable launch vehicles, the Saturn V, was not a sustainable space program. And they said, we better think about if we can do this with reusables. So now we've had 30 years of experience with reusables and said, well, that's too expensive, let's try expendables. And I think we may be starting to relearn how expensive it is to use completely expendable systems. So I will reintroduce the R word, reusable, into the discussion. Now, the other alternative is commercial crew services. Potential for high ascent safety if they're built on high reliability demonstrated vehicles. That we suggested that there should be a competition open to all. The White House seems to be going along this path. There are significant risks, both technical and non-technical. NASA should play the role of developing and enforcing mission assurance. And as further insurance, this is a quote from the report, heavy lifters should be developed that are human rateable, but not necessarily human rated, in the event the commercial systems fail to appear. So here is a chart which attempts to summarize our understanding of the benefits and costs or risks of the NASA commercial crew services. First, there are alternative sources of capital including private and corporate investment. Now, we actually did business plan level modeling of what a business plan would look like for a commercial entity to provide a commercial crew service, and with appropriate risk-weighted ROI for private equity at risk. My estimate is that the private equity would produce something in the range of 10 to 20% of the investment. Not 50%, not 80%. And that was the rationale for the then statements that said the government really has to incentivize, which is to say provide a significant fraction of the at-risk capital for the development, not for the operation. The commercial entities think that they could operate the system profitably. This is a little like developing a space system, then going bankrupt, and then operating it successfully, like Iridium. You know, it's hard to get over the capital cost, but if you have the system, you can actually make money at the operations. There are efficiencies which we argued about of corporately managed service provider business models. We took this in the range of, 0 efficiency to 10 or 20% efficiency. When a company has its money at risk alongside government money, it makes different decisions in a different way than it does if it's just government money. Right? That's the point here. The main factor is simplicity. That the good news is the Ares 5, the Orion, is a very capable capable capsule. The bad news is the Orion is a very capable capsule. When you fly a very capable capsule to low Earth orbit, you're paying for a lot of extra capability every flight. So of all of the savings in the commercial crew argument, the sort of easiest one to document is that you really don't need much more than about a 3-person Gemini to get to the ISS. And what we were going to do is build the capsule that would go to the moon, to Mars, and fly it to the ISS. Now, that was a strategy chosen by NASA under the previous administrator, one mold line in our lifetime. But when you saw the economic reality of it ripple through the system, maybe it's time to question that. And lastly, the amortization of the non-recurring and fixed recurring costs over other customers. Right? If the fixed recurring costs are a big part of the thing, and you're the only one who uses a launch system, and it's unlikely, despite claims to the contrary, we thought that anyone else would ever use an Ares 1 Orion. No commercial entity would ever buy an Ares 1 Orion at the true cost, or even a fraction of the true cost. Then NASA was stuck, would develop a launch system which only had one customer, which was NASA. They would actually develop 2 systems, the Ares 1 and the Ares 5. So if whoever it is that builds this commercial booster and this commercial capsule only sells one launch a year to someone else, NASA's share of the fixed recurring costs go down by 33%, because NASA's going to buy about 2 a year. Now, it's not hard to theorize that there's one non-NASA sale. Other governments, tourists, and in fact, there are people who spoke to us who think that by 2020 or 2025, NASA will be a minority customer, that there'll be enough other traffic to low Earth orbit. So it depends on the traffic model, and we all know you can jimmy traffic models to get any answer you want. But those are the rationale behind the economic decisions. Now, the risks, I believe, and it's well known that I'm a member of a board of a commercial spaceflight company, are actually not the technical ones. I don't think there's any doubt that commercial industry can build this system. I think the primary risks are the non-technical ones, like 5 years from now, the board of directors or the stockholders say, there's not enough ROI in that system, let's cancel it. Right? Or a supplier fails to deliver, or other. In either of these cases, it would require NASA intervention. And we actually went through in the report a fairly comprehensive what-if exercise of what if we went to an alternative, what should it be? So we thought about continued use of internationals, ruled it out. Thought of the use of the heavy, ruled it out. Thought of the ELV only if the ELV heavy is selected. So we got to commercial, and we said, but rationally, it's really too early to put all the eggs in the commercial basket. So there should be some strategy for a NASA backup, which we argued would probably be the creation of a human rateable heavy, right? Which would be a NASA vehicle, or maybe the core of a human rateable heavy, or something like that. There's also, one has to keep in mind that we were a committee that was responsive to policymakers, and the policy positions on commercial spaceflight are unambiguous. The guidance from OSTP, this is the paragraph that I showed you at the beginning of the talk, they only have 4 bullets in the high-level guidance, and one is stimulate commercial spaceflight capability. They wasted one of their 4 bullets on that point. And the Appropriations Act of 2008, I'm sorry, the Authorization Act of 2008 says, make use of U.S. commercially provided ISS crew transfer and crew rescue services to the maximum extent practicable. Right? There's not much mincing of words in that statement. And the appropriations language and National Security Policy Directive 49 also have similar language. So you have OSTP, national security, appropes, and authorization all saying basically NASA should figure out how to use commercial crew to LEO. This isn't an idea that our committee made up. These documents all precede us. So this line of reasoning gets us back to the integrated options that I showed earlier. And now I want to show you quickly some of the analysis we did on the integrated options with the help of Aerospace Corporation, although most of the assumptions that were made to cost these were made either by the committee or jointly between the committee and the Aerospace Corporation. So these, which are called options 1 and options 2, are the best you could probably do within the constrained budget. Remember, the president in his 2009 budget had given a run out for NASA that actually went down in real dollars for the first few years and then sort of gradually recovered. So we were asked by, it's one of the other 4 things that OSTP spent a bullet on, right? I just went by it. The last one, oops, I'm sorry, it's 45. Fit within the budget. And when OMB said fit within the budget, they meant fit within the budget that went down in real terms for the next few years. So now we're back to 47. So when you look at this curves, this is our estimate of what would happen in those budgets. The program of record, arguably, was terminate the space station in 15, the shuttle in 10 or 11. And when Ares 1 and Orion became available, fly it into low Earth orbit. Within that budget, you would get to Ares 5 by about 30. And there would never, ever be enough money to develop a lunar lander. That by the time you operated Ares 5 and Orion, you would absorb the entire human spaceflight budget. So that's the reference point from which the committee started its deliberation, right? That if you took the current program and put it in the current budget that OMB told us to fit within, you got nowhere. Now, if you extend the ISS and take the $2-ish billion or $2.5 billion a year that requires out of the human spaceflight budget, it only gets worse. And by switching to the commercial crew, you can sort of keep the Ares 5 and the Orion within the decade of the 20s, but just barely. Okay. So that's, subject to all the concerns about the aerospace costing analysis and so forth. That's the answer the committee had to look at. Now, if you look at the radar plot of those 2 options against the 12 criteria, it shows you that doing the commercial crew helps a little, but neither of those produce what the committee called a space program the nation would be proud of. So as a complete artifact of planning, the committee chose to bump the budgetary allocation up, ramped over the next 4 years to a bump up of $3 billion per year and then $3 billion per year thereafter over the president's budget. And we actually did some sensitivity analysis. We looked at it at about, unpublished, about $1.5 billion bump up, about $3 billion bump up, and about $4 billion bump up. And you didn't get much benefit from going to 3 to 4. And the sweet spot was probably around between 1.5 and 3. So we said, let's use the $3 billion bump up as the reference. So the findings on the human spaceflight options were basically, you can't get anywhere under the present budget. It's not viable, was the phrase we used. Meaningful exploration is possible under the $3 billion above guidance. So if you looked at the $3 billion above guidance manifests, the reference, which we call the implementable program of record, it put in some money to retire the space station and extend the shuttle a little, and otherwise left the program alone, would cause the Ares and Orion to miss the space station and a lunar lander to be in the landing to be in the mid-20s. This is the program of record with $3 billion more in the budget. If you extended the space station, of course it delays Ares 1 and Orion by a little more, so it catches the last couple of years of the space station. But taking that $2.5 billion for 5 years out of the funding in the teens moves the lunar landings to the late 20s. That's what I call option 3 variant. That does not appear in the report, and many people asked us why we didn't put it in the report. It basically just takes the program of record, extends the ISS, puts in the technology wedge, and otherwise executes it. And proposing, we just thought that proposing an option that did not have a credible opportunity for a lunar landing for roughly 20 years with a $3 billion per year increase didn't make sense to put down in writing. Okay? So the last one on here is what we call the Moon First Ares Light option, which puts the commercial crew in, extends the ISS, deletes the development of Ares 1, defers the development of Orion somewhat, and actually produces a lunar landing by about the same time as the baseline, but does have 5 more years of the ISS in it, mid-20s. And any of you who have done these sort of exercises know that the error bars on these dates are, plus or minus several years in most cases. So these charts are actually, as it says in some footnote, the beginning of the budgetary wedge starts at the 50% probability, and the end of the budgetary wedge ends at the 80% probability, because you hardly ever come in the first 50% in my experience. So these are the comparison against the metrics for the baseline and the Moon First. And you can see that the Moon First option with the commercial crew dominates the baseline program. That is to say that on all ratings it equals or exceeds it. So I'll give you a little tour so you can understand why. The Moon First with the Ares 5 Light has an edge in exploration capability. It produces a more, or would have produced a more capable launch system. It has an edge in technology because it makes an investment in technology. It has an edge in human civilization because this is where we bookkept the benefit of the ISS extension. It has an edge in economic stimulation because it engages the commercial community in the commercial crew. It has a benefit in global appeal because it extends the ISS, and it has a benefit in life cycle cost. So if you were going to use the existing pieces, that is to say, if your choice was really going to the moon and using the existing pieces or swapping out the commercial crew and putting in a technology wedge and extending the ISS, this would indicate that option 4A would be preferable to the baseline. Now, if you went to the flexible path, which were the options that started with 5, A, B, and C, and here, really the only difference is the launch vehicle. They all extend the ISS. They all have a commercial crew capability. See, so we were doing these traces through the matrix of decisions. Interestingly, because of sort of puts and takes, all of these end up with about the same schedule. And the puts and takes are that they have that the various launch systems have larger non-recurring costs or slower or lower recurring costs, or vice versa. And we put in a healthy program realignment cost, 10 or 11 billion dollars, if we went to the chemical system. Now, the other notable feature of this is that you get someplace beyond low Earth orbit by, call it the early to mid-20s with this scheme, and you only have a year or two-ish gap between the end of the ISS and when you can get someplace out of low Earth orbit. And that there would be this cadence going to the moon, going to Earth escape, the L points, going to the NEOs, going to a Mars flyby, where every year or so something new would happen. And then we chose to cost the option where by the time you went to the Mars flyby, then you decided to go to the lunar surface. So you did some flying around, and then you went to the moon with a lighter sort of lunar light system, and then you went to Mars. So we didn't find that the choice of the launch vehicle to first approximation was a big swinger in the schedule here. And you see it here in the spider plots for the three variants, which only differ by launch system. In some criteria, one of them has a little plus up, and with some criteria, another has a little plus up. This is really a trade study that could or would have been done. Now, this is the chart that I call How I Spent My Summer Vacation. Because the blue curve on the spider plot on the right represents our assessment by, admittedly, the criteria that we developed, but based on those in the global exploration strategy. The blue curve represents the baseline program as we received it, with a plus up of $3 billion a year. And the red curve represents, if you will, the option that in our system scored the best, which was the flexible path with the Ares 5 light. Although the flexible path with the EALV-based vehicle didn't vary from that by very much. So you can see by reading down the bullets on the left-hand side that in almost every of, in 9 of the 12 criteria, the flexible path mission exceeds the baseline, and in 3 of the 12, it exceeds it by 2 steps. Exploration, preparation, economic expansion, and global partnership. Right? So in a 5-point scale, to get something that's 2 ticks above something else is a pretty significant jump. Now, a lot of the reason why the flexible path scores well, in addition to the fact that it does things that it takes humans to places that humans have not previously been gone, is completely explainable by this simple cartoon, which is if you go to the moon first, if anybody goes to the moon first, they face the programmatic bulge on the upper chart, that you have to develop the capsule, you have to develop the booster, you have to develop the lander, and you have to develop the lunar surface system, all before you really get any value of going to the surface of the moon. And if you want to see a budgetary wedge that does that, look at the NASA budget between 1961 and 1971, where in 1966 it peaks at 4.5% of all federal expenditures. Right? And then multiply by 1.3, because Apollo did not build a lunar surface infrastructure. So there's roughly 4 pieces that you've got to do. They're of comparable size, although this cartoon is actually drawn to give some indication of scaling. The surface systems is arguably probably the least expensive of the 4. So maybe you multiply by 1.2 or 1.25. That's the bulge that you need to efficiently go to the moon. Okay? We don't have anything like that. So if you did the moon and then you did the flexible path, you'd spend all that money to go to the moon, and then you'd spend just a little bit more money to build like an in-space hab, and you'd go along the flexible path. If you went along the flexible path first, what you'd do is you'd build the capsule and the booster and the in-space elements, which are quite modest, handful of $1 billion rather than 30 or 40 billion. And then you'd get value by going to L points and going to NEOs and going in Mars flyby. Over here, here's the American public looking at the right hand while you're doing all this thing. And over here, you're then taking the capital budget of NASA and you're building landers and surface infrastructure so that 5 or so 6 years into the flexible path, you now have the landers and the surface infrastructure to explore the moon and Mars, or the moon or Mars. So it's sort of something that almost every program manager I've ever showed this to looks at it and says, oh, I see. You basically build the parts of the system that allow you to get some value while you build the rest of the system so you get the rest of the value, rather than having to build all the system before you get any of the value. And that's really the magic, to the extent there is any. Now, behind the scenes of this 12-point criteria, there was some stakeholder analysis that my group at MIT had done. Statement of the obvious: a sustainable program focuses on frequent and intentional delivery of value to stakeholders. And in fact, NASA 7123.1, principally authored by the existing associate administrator, says in sections 3.2.1 and 3.2.2 that stakeholder analysis and the derivation of high-level program goals from the stakeholders is mandatory. Okay? So this isn't an idea that we thought up. This is an idea that your associate administrator thought up when he was the chief engineer. So the problem is that the flow of value to the stakeholders in exploration is extremely complex, and you really have to think about it carefully and maybe even model it a little to understand it. We have developed a method, now being careful, we being my group at MIT, a method of closed-loop stakeholder value network analysis so that one could help understand this. So again, don't have time to go into this, but would be more than happy to come back and talk about this or any of the other topics, Mike. This is what we perceive to be the ideal stakeholder value flow from NASA exploration enterprise around through the network. And this is drawn like that famous map of Napoleon's march to Moscow and back. So you know, we read Tufte too. So the width of the line is the importance of the flow, and the color of the line is the nature of the flow. And basically what it says, if you look at it for just a few minutes, is that almost no benefit derives back to NASA directly from any stakeholder in exploration. That benefit flows from NASA to stakeholders and then to the other agents, including the American public, and then to the Congress and the executive, and then back to NASA. That this is really a closed-loop system, and you have to think about it as a closed-loop system. And basically, these are representatives of the gains on the loops. They're the loop gains, right, of the nodes of the propagation of the signals through the system, right? So if you believe this is true, then you can use it to sort of rationally say, what would a sustainable exploration program do? It would engage the science community. Well, you know, now I can say each of these, and then you can say, did Constellation do this? You know, it should engage the science community. Did Constellation do this? It should include the space commercial economic sector. Did Constellation do that? It should engage the educational community. Did Constellation do that? It should engage the media. Did Constellation do this? I'm not making value judgments. I'm just saying that the Space Act of 1958 as amended actually enumerates those as the stakeholders of NASA, not the media, but the media as a surrogate of the American public. Right? You don't have to look very far past the first 3 or 4 paragraphs of the Space Act to find the congressionally enumerated stakeholders of NASA. Other government agencies, the Defense Department. Did Constellation engage the defense community so that, like in the shuttle, when it came under budgetary pressure, the Defense Department was there to help protect it? You know, the re-engineering of the KC-135 was deferred for 3 years to produce money out of the DoD budget to pay for the shuttle by the Secretary of the Air Force. So you can do that sort of analysis. I don't have time to do this, but it gets you with it gets you to a set of high-level requirements derived from stakeholder analysis for a sustainable exploration program that are not a traditional NASA view. Things like the most important thing is participatory exploration. You know, if the political rationale is that we do this to stimulate the youth, then we damn well better have a program that stimulates the youth. Right? Because otherwise we lose that rationale. If part of the rationale is that we develop technology not only for NASA, but for other space-faring agencies of the government, then we should consider whether we're doing that, and so forth. And high on this list is, you'll see it's the third and fifth bullet on the left-hand side, are steady cadences of progress. Are the American people and the media, their representatives or their conduit to them, going to actually see from our exploration program a cadence of new things happening each year? You know, because we remember, you know, 2 things about Apollo 13. You know, one is that it blew up and we almost tragically lost 3 astronauts. The second was that the explosion occurred shortly after the first news conference from space that was ever not carried live by the media, because we'd already gone to the moon a couple of times. They weren't even carrying the news conferences from space anymore. So the summary of the integrated options, this is sort of the summary of much of the report. Exploration doesn't appear viable under the FY10 budget. Fly out the shuttle, extend the ISS, further develop a robust commercial space industry. There are two paths to exploration strategy. Both could be done. One makes more sense programmatically because the flexible path has quicker return. Other findings, robust technology program. We knew that that was important to this administration, and we put it in all options that when we could. Involve international partners. I have to tell you that the input we got from the international partners weighed very heavily on us, on the committee. Most of them spoke about the need to extend the ISS as the dominant theme. But not too far behind that was the theme that they would really like to participate in an international endeavor of human exploration led by the United States, but they'd like to participate and not be told what to do. The process of engaging them in the planning is very important. Now, there's political realities that, the Hill and the OMB want an answer in I don't know how many days you have left.
We're late.
Yeah. So this is a conundrum. This is a tough one. How do you structure a process over the next year or two where you feed the domestic political organization what it needs while engaging the international political organization? That's not an easy nut to crack. But that we should engage the internationals is really pretty serious. And I'll tell you, we also wrote a fair amount in the report about the NASA management challenges and that the administrator should be empowered to run the agency. And the last line, which is actually the first paragraph of the report, says the fundamental thing we recommend is that NASA be given a budget and a mission that are aligned and not pretty pictures of things that it's expected to do and not enough money. That there has to be reality and expectation and resources. And that we adamantly refused to write a report that said NASA could do all these wonderful things on the budget that it was given. That if anything we did, we tried to put realism into the discussion. Maybe we'll be criticized for putting realism into the discussion. That NASA was on, quote, an unsustainable path, end quote, from the report. I just wanted to come back and give you a little look forward. Now I've more or less ended the summary of the report and what we did last summer, but I can't help but do a little forward looking here. Now that we've made the decisions that one would that have apparently been made, we probably have something like the launch vehicle on the left that goes to low Earth orbit. I'm assuming that we have some sort of new booster upper stage combination. We recommend, as I said, that it be built large enough so that it has some initial capability of escape, some payload to escape, but then is significantly supplemented, order of 2 to 3, by a refueling capability, in-space propulsion, CEV, in-space HAB, and then eventually landers. And you can see my preference for, let's go back one, my preference for the flexible path timing shows through in the drawing of this figure. Now, this is too busy a chart for most of you to see, but the point I'm trying to make on this chart is that we want to make a sustainable enterprise, and that to the greatest possible extent, a sustainable enterprise will come about if we have an architecture that's flexible, that includes a consideration of commonality, and possibly even a consideration of reusability, as the note in the lower right-hand side. So, for example, in the Shuttle C days, there was at least a discussion of building a boat tail that returned the SSMEs on the Shuttle C back down. We're not going to build a fully reusable vehicle, but could we figure out how to reuse, some of the high-value components of the boosters? Could we figure out how to refurbish the crew capsule? could we figure out how to refurbish the HABs that always stay in space while they're in space? That's what I mean by reusability, as opposed to building Shuttle 2, which I don't think we have the funds to do. So if you look at the sort of lighter green, I've tried to indicate where there could be flexibility in the system. Flexibility is you build a set of things, and then they're useful for more than one mission. So starting on the lower left-hand corner with A, these are lettered, you could build a core plus 0, 2, or 4 boosters. This is an old trick. We know how to do it. We could build an upper stage with a short and a long version, stretch and a 737-200 and -400. We could use the ISS, at least initially, as the base for orbital refueling, on-orbit refueling. We have a space station. A fuel depot is a small space station by another name. It's a small unmanned space station by another name. Maybe at least initially we think about fueling on the space station. The likelihood that we will go through the international process and not end up in 51.5 is small, in my opinion. Right? Just a statement of fact. We can build modular or stretched in-space habitats. The word habitat up there in D. It's the in-space propulsion system. So we could build a modular or stretchable in-space propulsion stage. No thrust to weight considerations once you're on orbit. We could build a modular or stretchable HAB for shorter duration missions and longer duration missions. So there's a lot of potential of flexibility. Then there's commonality. Commonality is using the same thing between two systems, right? So you start again down in the lower left-hand corner. You could reuse the launch system with other customers, right? You could build a system so the core of it could be used for national security space or potentially even communicate. You could use the same engine on the core and the booster, which I would argue we should examine both LOX, both liquid hydrogen and RP1 for the first stage. We could build the core and the booster on the same line. We could use the same engine on the upper stage and the in-space stage. Right? And if we use the same engine on the upper stage and the in-space stage, be it either hydrogen or methane, then we could use the same technology for long-duration storage on both the depot and the in-space stage, the in-space stage has to store fuels for 600 days. Right? So, once we decide on a hydrogen economy or a methane economy below Earth orbit, we should stick to a hydrogen economy or a methane economy below Earth orbit. There's the unlikely but possible extension of the CEV from the commercial crew. There's the same engine on the in-space stage and the lander. This was actually something that was in ESAS, right? That Fragola and others argued that the only way to get sufficient reliability on the descent stage of the lander was to already have pre-used that engine on the in-space stage. Right? So that's actually something that was in ESAS and drifted out of the system, but is actually a very sound idea. Now, it requires you to build an in-space stage that also has a throttleable variant, which is an additional complexity. You can use the same lander on the Moon and Mars. You can use the same lander for cargo and crew. So I guess my question to you, Mike, since you're running the integration team, is who is the architect of that system? Because one thing we know from the study of commonality, another ESMD-sponsored activity that we've done in our lab, is that if you break that system up into 6 or 8 pieces and send it out for analysis and then staple it back together, there will not be that commonality. There'll be 6 engines there rather than 2 engines. And there'll be 5 stages rather than 3 stages. Right? And I don't think that we're going to have the money to do that. And in fact, as I just mentioned, commonality is something we've studied. I'll just finish up here briefly in the next minute or two. But there are essentially 3 tests, and something that NASA has done very successfully. I mean, the upper stage of the Saturn 1B and the Saturn V were the same. The guidance computer and the LEM and the command module were the same. The J2X was going to be common between the Ares 1 upper stage and the Ares 5 upper stage. this is not new, but to do it, we have to make sure that the commonality is technically feasible, and we've actually developed under your sponsorship tools to help and analyze that. It has to be managerially implementable, right? That is to say, the management structure and the management incentives have to reflect it. And it has to be financially beneficial. And in fact, we're working with Arlene to develop costing tools which allow us to reflect it. So I'll skip the next few in the interest of time. They just basically said that. So I'm teaching a class this spring called Advanced Space System Engineering at MIT. And we did a little theater because the first day of class was the first Tuesday in February, which happened to be the day that John Holder and Charlie Bolden had their press conference announcing the new budget. So I flew to Washington and went to the press conference in the morning and flew back to MIT in time to teach a 2 o'clock class. And I walked into class with a real handwritten note from the administrator saying, students, we've been asked to design the architecture of the new exploration system. It was a nice piece of theater. Right? So I have a group of 15 or 18 students who are actually doing this in real time in Cambridge at no cost to the government. And one of them claims that this is the diagram that I wrote on the blackboard that day, but I don't remember it, doing it, but it's not a bad place to look at. That if you had to think your way through the process that you are engaged in, you should start with goals. What are the goals of the human exploration system? That would lead you to an understanding of destinations. That would lead you to an understanding of architectures. But the understanding of architectures is sensitive to the investments made in technologies, which is the sort of second line. That we have to look at the sensitivities of the technologies. The combination of the architecture of the technology informs what systems we'll build. The architecture informs the sequence, and the combination of the cost and sequence and systems informs the schedule. And in that right-hand side, you're in the iron triangle. And I can make two statements about this. One is, you don't really want to be in the iron triangle, right? You don't want to be in a position where you're promised performance, budget, and schedule for a highly complex and unprecedented system, because all experience shows you won't make it. On the other hand, the Congress is yelling at you to give them the dates and the destinations, which is basically forcing you into the iron triangle. So along with the international conundrum, this is the other one that I would say you have. A rational spokesman, and if asked by members of Congress, I actually say this, would say, you got to give NASA at least a year here to sort through what's going to happen, what reasonable costs are, what reasonable timetables are, and you've got to ask them to produce a set of metrics by which they can be measured in progress along the way. But that's not an easy political message to convey. They want to know where you're going and when you're going by, and that's a lot harder. So I'll remind you of a few historical facts, and then I'll get off the stage here. When the president asked NASA to go to the moon in 1961, NASA commissioned a study of how much it would cost, and it got to Bob Seaman's desk, and he doubled it. And Bob then took that number and he gave it to the administrator, whose name is slipping my mind, Webb, and he doubled it. And that's the number he presented to the Congress, and that's about what we did the program for. In 1961, the schedule for going to the moon showed the first landing in 1965. And the first landing was, of course, in July 1969, which is about twice as far from 1961 as 1965 was at the time. So in Apollo, the schedule doubled and the price went up by 4 from the engineering estimates of those quantities. So it's a little sobering, but we can't put ourselves in a corner. So I'll just put back on the last chart, which is the strong feeling of the committee that, you know, there really is a vision out there of a destination to go to, and that we should be working towards that vision. Well, thank you very much for your attention.
All right, thank you, Ed. I know we ran a little bit over time here, but there were a potential couple questions. I think we can allow, actually at this point, folks can drift off as they like, but if there's any questions anybody would like to feel free to ask.
Yeah, and I'm happy to stay around for as long as it takes.
Hey, Ed, Chris Colbert.
Hi, Chris.
How deep did you take in the strategic analysis? How deep did you take some of the commonality discussion?
Not very far, Chris. You know, because we did what anyone would do with this amount of time that we had last summer, which is we asked one team to do this and one team to do that. But then we on the committee, or on the technical working group within the committee, which included me and Jeff Grayson and Bo and Chris Scheibe, someone I'm leaving off. Who else was in the technical group? It was principally those four. You know, we tried to look across these things and see opportunities for commonality, which is what I tried to present on that chart. We certainly didn't do any detailed analysis that indicated that that commonality, how much commonality could be achieved. But we mostly cited, you know, the study last summer was really not a study, it was a meta-study.
Yeah.
I mean, in you know, 60 days you don't have time to do studies. What you have time to do is collect the previous studies that have been done and look across them and learn from them. So, you know, there are a fair number of studies, Delta Atlas V Phase 2 Heavy, for example, that have looked at, you know, commonality between a hydrogen booster and a hydrogen core. I cited the ESAS study that had commonality between the lander engine and the now called Orion engine, or what would have been the Orion engine. You know, so there weren't any of these cases where we couldn't have found some precedent.
Yeah, I guess where I was going with the question is, from the perspective of building an architecture, the benefits you get from commonality frequently don't show up until you go to a lower level of detail than the architecture commonly captured, right?
That's right. And not only that, but the trend is that at the higher levels you assume that there's more commonality than is actually achievable, and then as you go into detail it tends to erode. The word we use is diverge. That, you know, the commonality plan often for good reasons tends to show less commonality. We've done a thesis that has or paratheses that have 10 case studies of this, including 3 done within NASA, and you see the same trend. The best documented one is the JSF, where, you know, commonality was a fundamental part of the cost containment structure, and they were originally promising levels of commonality as high as 50 and 60% amongst the Air Force, Marine, and Navy versions of the vehicle, and it's now down in the 20s and 30s of percent commonality. But it's still there, and there's still significant cost savings resulting from it. So one of the things you find in the management of commonality is the way to get it is to start with a relatively high goal and have a mechanism for sort of at the system level controlling it, you know, sort of like a commonality control change board, so that if you want to deviate from a common system, you have to come and present a rationale, and then of course the change board can let you off if there's good reasoning. But it's sort of like it's like entropy. You know, the system tends to go towards more disorder, which is to say not commonality. So to get it, you have to start with the goal of a high amount and have a controlled process to let it erode away.
Yeah, and in a discussion like this, that high amount has to be managed more at the architectural level than at the systems level, because each system will optimize within their own domain as much as they can.
That's right, and you're exactly right. And the other artifact that we observe, this is the work we do with Arlene, is that when you actually lay out the commonality between, let's call it system A and B, the first one and the second one, that that system A sees almost always cost, and almost all of the benefit to the combination of A and B comes when you build B. So if you're the program manager for A, this commonality stuff is just a tax. And it's only if you're at the architecture level that you see that if you do it in A and B, you get a net benefit. For example, if you were the manager of the in-space propulsion stage, you knew that you could run your in-space propulsion engine at 100% thrust all the time for your mission. You know, to build in the capability of a deep throttleable engine would just be a cost. But then when you went to build the lander, you know, there would be enormous benefit from having developed a deep throttleable in-space engine and having it already demonstrated to be a reliable engine. It would save millions and hundreds of millions of dollars of testing time. So you're right, you're absolutely right, and it's only a little worse that when you time-phased development, you get this additional penalty, if you will, or this additional factor that the first guy, the first program manager, almost always sees tax, and all the benefit is in the, he almost always sees cost, and almost all the benefit is when you do the second thing.
So Chris and Mike and others, we want everyone to know that we have the MIT Group Vets group under grants currently to be continuing these commonality studies. It's not just the identification of technical commonality candidates, but the more fundamental management issues, addressing these at the architecture level, also addressing these early enough so that you can affect procurement and overall strategy development. So we have assets that are disposable to study this more. The extent to which we incorporate and use this analysis, of course, is entirely up to us. So, okay.
But we're happy to cooperate.
Ed?
Yeah?
I'm curious about the discussion of hydrogen versus methane economies.
Yeah?
And I was wondering to what extent did you discuss that, and have any of the recent discoveries by LRO informed that trade anymore?
I'll pass on the last one. You know, you go to the moon, there might be some reachable hydrogen. You go to, and oxygen, you go to Mars, you know, there's carbon, hydrogen, oxygen, you know, depends on sort of where you think you're going to get stuff. You go to the, I would say one of the things that we didn't spend enough time thinking about last summer was what ISRU at NEOs could produce. You know, what's in a NEO, how recoverable is it? You know, a lot of it's regolith. Regolith in a NEO might or might not be the same, have the same things as regolith in the moon, you know. With regard to the hydrogen or methane economies, I would say we discussed it some. Mostly we discussed it with NASA people. It's interesting, for example, that the Altair was a hydrogen lander. But, you know, in talking with John Conley, it was pretty clear that in his next cycle or so, he was going to go and look pretty closely at a methane lander. And don't know how that would have traded, but it was certainly sort of on the list of things to look closely at. Because these hydrogen systems, when you have to operate them for hundreds of days in space, with, you know, at hydrogen below the boiling point of hydrogen, and you deal with the density of hydrogen storage, you know, they don't look as attractive as long-term in-space things as they do on the pad, I think is the simple way to do it. So, you know, in my thinking, there's sort of two mixtures that make sense. There's RP1 for the first stage and booster and hydrogen for the upper stages, which would then probably suggest that you want a hydrogen economy. And there's hydrogen for the lower stages, which is sort of what NASA has done for decades now, and methane for the upper stage, which then sort of leads you to a methane economy. And when you do the trades, you know, RP1 plus hydrogen on top and hydrogen plus methane on top actually sort of usually produce similar performance. Of course, hydrogen plus hydrogen beats both of them, but produces lots of hydrogen engines you've got to develop. And, you know, RP1 plus methane is not really you know, it's got sufficiently poor performance that it's really not probably a viable tender. But I would think very carefully, and I actually noticed in rereading the report in the last few days that we probably didn't help you, we, the committee, probably didn't help you, you folks who are doing this now, by being maybe a little more specific in a couple of paragraphs in the report than maybe we should have been about suggesting an RP1 based first stage as the desirable solution, or as a desirable solution. We probably should have left a little more fuzz on that discussion, because I would certainly be looking at hydrogen plus methane in the upper stages, which then produces methane in space, or RP1 in the bottom and methane on top, which then sort of leads to methane. I said that wrong. One of them leads to hydrogen in space. You know, if you look at the boiling points of oxygen and methane, which aren't that far apart, you know, and you look at the sort of equilibrium temperature of a spacecraft that's in rotisserie mode in free space away from Earthshine, you know, you barely have to cool oxygen and methane. It's more of a fluid management problem, whereas hydrogen down at, you know, tens of degrees Kelvin, you know, you're always actively managing for the entire lifetime of the mission.
What about the end state, though, if I want to go to Mars, do another person's chemical trade, does that drive you?
Not obviously, because I think the range of performance that you get out of the nuke is so broad, depending on the assumptions you make, that you can sort of make everything look good or everything look bad. You know, I mean, there's enough knobs on the design of a nuclear thermal or nuclear electric stage that it could be a big win or a big loss. I mean, I think that the real issues involved in building a nuclear stage are really in other dimensions. You know, can you build an autonomously operating nuclear reactor that reacts in the absence of human intervention for 5 years, which has never been done, right? You know, it's not the fissile plant that's really in controversy. It's all the stuff that makes it into an engineering device. You know, are you going to get the political clearance to launch it? You know, when you do the system level analysis, there's no doubt about the fact that a well-designed nuclear in-space stage beats a chemical one, right? Hands down. I mean, even if it's only an ISP of 600 or 800, it still does much better. And it has a significant amount of thrust if you do nuclear thermal. But, you know, if you look at DRA 5.0 and you look at the sort of 10 or so Ares 5s that you need for a chemical system, and you look at the 7 or so Ares 5s that you need for a nuclear system, the benefit that flows through the system is that you didn't launch 3 Ares 5s for each Mars opportunity. About 3 is about the difference. So the question is, in view of our understanding of the real cost structure of heavy lift launch vehicles, where much of the cost is fixed recurring, and only really a smaller fraction of the cost is marginal recurring, you know, does the change from buying 6 Ares 5s or whatever we replace it with every 27 months to buying 10 Ares 5s every 27 months, do you ever recover an economic benefit from that justifies the capital investment in the nuclear plant? I think that's really the question. Now, that assumes that you also have, of course, you know, the chemical one also assumes you have aerobraking and aero entry, right? So, you know, you have to staple those two together as well. You have a chief technology officer who believes in aerobraking and aero entry. That's the good news.
I understand that when you were taking a look at some of the science aspects of the demographics could have been just a little bit limited in your information. So I was curious if you could comment on the rigor that you would use to find out the needs of the science and other users that either were considered or need to be considered in future architecture?
Yeah, I'm not quite sure I understand your reference to the rigor of our approach. I'm sure that once a report comes out, many people are critical of many things, but we tried very hard in days of testimony to hear both public and fact-finding, to hear from the scientific community. And I think we did the sort of obvious thing, which was we went to the National Academy and asked the chairman of the appropriate science advisory committees to talk to us. Some people may think that they're not representative of the scientific community, and I'll pass on that point. I think the most important thing to say about science in the exercise that you're in now is don't commit the mistake that NASA has sometimes committed of pinning the rationale for human exploration on science. The scientists have antigens, antibodies against that as soon as you open your mouth. That you have to be very respectful. One has to be very respectful, and we tried to be respectful of not ascribing to the scientists their support of human spaceflight missions, of walking a fine line between saying, you know, science could be done on these missions, which is valuable, and saying science justifies these missions. So if we take the lunar example, you know, most planetary scientists would say something like, if there is human exploration of the moon, there is important and valuable science we can do there. Or Steve Squires said at a public hearing that, you know, that humans are very important in unexplored, complex environments where judgments they make in real time can add great value to the exploration. You know, that's about as strong a statement as we extracted from the scientific community in support of human spaceflight. You know, and Steve Squires built things that rove around, and he knows how hard it is to drive them. You know, so if you read the report, we were very careful to say, respecting the legitimate priorities of science and doing science that appears amongst the priorities of the scientific community, and words like that. And you know, we had sort of two canaries on the committee, Charlie Kennel and Chris Chiva, who were our card-carrying space scientists of different types, who would constantly remind us that, you know, the priorities of the scientific community usually do not, as developed within the scientific communities, usually do not strongly support the human spaceflight endeavor. So that you can take credit for it as, if we do this human exploration, there will be scientific gain. But one should be very careful to say that science justifies this human exploration. And I would say that was the main finding with respect to science. Now, you know, the details of, you know, were there scientists who might have said that destination X was more important than destination Y, or destination Y was more important than destination X? Almost certainly. Just like there were many people who came to us that said Rocket 1 is better than Rocket 2, or Rocket 2 is better than Rocket 1. And when you're in one of these exercises, you have to listen carefully and think wisely and speak carefully. And that's what we tried to do. Now, to directly answer your question, I can think of several different mechanisms for engaging the scientific community. I have to now preface all this by saying I'm not a scientist, so you know, this is just an engineer talking about how to engage the scientific community. But you know, there are established committees of the National Academy. Scientists enjoy open forum where they can come and, you know, and speak and talk. There are established professional bodies, you know, the American Physical Society or an American Astronomical Society and so forth, with whom it would be useful to engage. But when one engages in those broader scientific forums, you know, you hear many diverse views. about what's more important and what's less important. So in the short period of time that we had, I think it's fair to say that we used the National Academy as the filter. And we said, the National Academy is where scientists come together, argue amongst themselves, and produce a peer-reviewed report on priorities. And that's, and in the amount of time we had, looking at the peer-reviewed report on priorities is important. You got to go.
I have to depart. Thank you very much for your time. You all free to stay and engage on questions. We are going to follow up on this in a couple areas. I do know, Phil, we do want to get with you all, since you were the executive secretary for the Augustine work, on the data repositories and this analysis information. Because some of this is, actually quite a bit of this is information in good context that we didn't get out of the report.
Yeah. One of the reasons why I offered to Mike to do this was to at least provide pointers to some of these studies which are likely not really archived very well. I mean, they're all on somebody's laptop, but none of them are on his laptop.
And then the second part, Ed sort of left the unanswered question in the room about the architecting effort. Of course, as we're all well aware right now, we are not doing any degree of architecting today. We're trying to respond to the new plan and vision and get our budget programs in order. We're kind of reaching the point, though, where we're getting the OMB deliverables done. We're getting at least the pre-formulation plans together for the programs. And so now it's kind of time to take a look at that longer-term architecting effort and how NASA's going to approach that.
Right.
And all the planning so far shows that it's going to be not an ESMD-led effort, but probably a larger NASA-wide.
Mhm.
So we'll have some further engagement on that
Right.
as well.
Okay.
Thanks.
Well, thank you.
Hey, Mike, one quick thought. Don't forget the internet. We are actually doing some architecture. We're wrapping up the lunar architecture of the International Committee right now. So we do have some things going on, but we don't want to forget that international piece as this spreads out beyond ESMD.
Agreed.